All right, so number 2, we're actually going to use the same information, the same table here for questions 2 through 5. And I'm really excited about this problem. I mean, not just this particular problem, but the series of problems that we're going to look at here, because we really are getting an opportunity to do some real math. So it's not just some random x's and y's and some numbers, and students always ask this question, why do I have to learn math? What's the point? When am I ever going to use this? So what I don't want you to be afraid of here is that don't think of this as a word problem. So you've always wondered, well, why do I have to learn math? Well, so don't be afraid of the context. All we're doing here is that we're just introducing the same numbers, but instead of them being some random numbers that have no meaning, all we're doing is just putting a context or a story along with it. And so I think by looking at it within a context, I think what we're going to do over these next couple problems will make a lot more sense to you versus if I just thrown some random numbers up there and you're like, well, what does that have to do with anything? So, like I said, don't think of this as a word problem, and in the end, I think hopefully it'll make a little bit more sense. So on number 2, or at least 2.1, the information that we're looking at, if you look at the table here, says child's age and annual cost. So, and this is 2003, so maybe the numbers are a little old there, but probably not too far off. And what we're saying is that if you have a 3-year-old, that on average, that 3-year-old is going to cost you $10,700. Just in that 1 year. It's a lot of money. A 6-year-old would cost you $11,700, and then what you're noticing is that as a child gets older, and here's, hey, maybe you, right? Maybe you're 15, maybe 16, 17, close to that age. That's a lot of money. That's a car, right? Now, where are they getting that number from? We're including obviously the cost of clothes and food, and at a younger age, perhaps daycare. Health expenses, those sorts of things. Obviously, too, living expenses in terms of, more kids. Maybe you got to get a house or an apartment that has an extra bedroom. So all of these kinds of things are getting figured into these numbers. So what we're going to do is we're going to take those numbers and then kind of do a little analysis, or try to see if we can pick out some patterns from the numbers that are there. Well, the first way to see a pattern is to have a picture of it, right? And so that's what this graph is. A scatter plot is kind of the name suggests, scattered. Scattered means it's kind of spread out. And so I think that's what you'll see with the points here. So the child's age represents X, and the annual cost represents Y. So let's get this thing labeled here. So we'll say this is child's age. Actually, let me move my graph a little bit. I think I'm going to let's move that up just a little bit. So child's age. And you notice here it's got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The child's age goes from 3 to 15. So what you can do is you kind of calculate the spread there as far as how far the numbers go out. And so probably counting by twos. So let's count by twos. So we've got 2, 4, 6, 8, 10, 12, 14, and 16. And this is just a sketch. So what we're really looking for is just kind of picking out a general pattern. So it doesn't have to be super duper accurate at this point. We just want to be able to see a pattern that's going to emerge. Along our y-axis, that represents annual cost. And again, I think it's interesting to keep in mind here is that we're not just talking about how much that kid's going to cost you over the course of, let's say, their lifetime, or from a baby to 18. We're saying in 1 year, that's how much the baby is going to cost. And then, so if you look at the cost, now obviously the costs go from 10,000, 16,000, and I've only got 10 squares here, so I can't count by ones or twos. So what we're going to do is that we're going to put a little break in the graph. And so you notice what I did there is I just put two little parallel lines. And what that's saying is it's saying that I'm going to jump because again, I can't just count from 1 to all the way up to 16,000. So what I'm going to do is I'm going to do a little bit of a jump, and I'm going to jump up to 10,000. And then what I'm going to do is that for each line, I'm going to jump 1,000 from there. So all I did is I just put a little break in the graph because I've got only so many lines, and the distance here from 10 to 16, so that's pretty close. So I can just count by 1,000s, and 16 and 17. All right, and so let's plot these points. So the first point is 3, 10,000, and and if it helps you, you could rewrite these things because this is really what it's saying. I know that the table is written horizontal or it's written across, but really this is, if we wanted to look at it another way, these are the ordered pairs, or these are the points that we're going to be plotting, right? And so the plot part, that's where the scatter plot comes in. And so 12 and 15,000 and 15 and 16,700. So let's see, our first one there would be 3, 10,000. So 3 would be in between 2 and 4. 10,700, it's a little bit more than halfway up to that box, and then a little below. Like I said, so this point, this part isn't, it doesn't have to be perfect. We're just looking for a general trend. And we'll see here in a second what that trend might be. So 12 and 15,000. And then 15 and 16,700, something like that. All right, so what are the general trends that we're looking for? Well, first of all, what's the direction, right? Does it look like it's going up, down? Well, it looks like it's going uphill, right? If we were to kind of, the dots are not exactly in a line. That's why we call it a scatter plot. So it's not exactly in a line, but you could tell for the most part that it's going uphill, and that it is a line, right, versus any other kind of shape. So it doesn't have, it doesn't have a shape like that, for instance, and that's another type of function that we'll look at pretty soon. But for the most part, it has a straight line. Let me take that guy off there. All right, so that's really what we wanted to see in this first part of it, was labeling the x and the y, right? So we wanted to get the x labeled, we wanted to get the y labeled. And then deciding what to count by the way, is what I did is I had 10 squares, and so I kind of took the difference and I just said, well, what could I count by? Now you may, on this next couple problems, you may choose to count by something slightly different than what I did. That's okay. But you will put a break in each one of these. So just how we put a break and we kind of jumped, you'll put that on yours as well. All right, so pause the video now, try 2.2 and then 2.3, and let's see if you can come up with a scatter plot for those two situations. All right, so let's go ahead and look at 2.2. And you might have been confused as far as how to label the graph. The thing I would tell you, and let's look at 2.2, is that you're just trying to get all the numbers to fit. Sometimes the graph will be labeled for you, sometimes it won't. So in this case, it wasn't labeled for you. So you're just having to decide, I got 10 spaces, what would I count by to make sure everything fits? So from this case, I count by tens. On this one, because the numbers are so large, we can't, count by tens up to 755,000. So what I did here, by the way, is that I did a break, and then I was like, okay, I've got, after I do the break, then I've got 9 spaces, so how can I get it all to fit? So I just counted by 50,000 increments. And you notice, by the way, because the numbers are large here, we're talking about price of home values, so I wrote 800, that's really 800,000, 750,000, and so on. You notice the trend here on this one is that it goes downhill. That should make sense because what we're looking at is the distance from New York City and the price of a 3-bedroom home. So usually if you're right in the middle of things, then real estate values, that's where you're going to pay a lot more to be right in the middle of all the action. As you move further away from the city, you usually get a little bit more for your money. So we can expect that right dab in the middle of Times Square, we're going to pay a lot for that, versus if you go out into the country away from Manhattan, that you're not going to pay as much. And that's not just for New York. I mean, that's really any city, Los Angeles or any other large city. So that's what your graph should look like for 2.2. And then on 2.3, what we're looking at is grams of fat in a sandwich and calories. So we're looking at the relationship. If a sandwich has a certain grams of fat, how does that relate to the calories? Well, basically you can see that the more fat a sandwich has, no shocker here, the more calories it's going to have, right? So if it has a lower amount of fat, you got less calories, whereas if it has a bunch of fat, you can expect something that has a higher calorie. So again, something that's going uphill. It's not quite exactly a perfect straight line, but it's close enough that we could say that it's linear versus any other shape. All right, so those are the scatter plots, and then what we'll do for questions 3, 4, and 5 is we'll refer back to these pieces of information.